Hey there. In this module, we're going to discuss repeated measures analysis of variance. In this video, I'm going to give you a brief overview of all the things available in the module and do a brief lecture on repeated measures, ANOVA. I would start with the module with this README file. In the README file, it lists all of the assigned readings, some optional readings to kind of get you started. So this lesson will follow the Graviter and Walnu chapter 13 on repeated measures, analysis of variance. If you have another book like the Hinkle book, I believe the repeated measures, there's a repeated measure section in just the ANOVA chapter. So if you have a different book, you might just have to flip to the index and find repeated measures analysis of variance. But I've also tried to provide you a lot of additional resources. This is a great overview of repeated measures, ANOVA. Here's a journal article describing repeated measures, ANOVA. Here's another guide on, especially goes into detail on the sporosity assumption that's made in repeated measures, ANOVA. And here's an extra document that I made that discusses some different alternatives to repeated measure analysis of variance and talks about some of the advantages of using some of these alternative analyses and where you can find some more information sort of about them. So you can read that. There's also some optional readings here. If you feel like what you've read before isn't quite, you're still kind of confused, I've added a lot of different optional readings. And if you get to some of the readings you feel like, yeah, I really know this, you don't have to go through every single thing, but I want to just be sure I provided you with enough information. There's also links in here to the assignment and quiz, which you can also find in the module, listed down here in the module. All of the non-textbook readings, I've also combined them all into, you can download them here in this zip file, so you can find all the required and optional readings in there too, so you can download them all at once. Here's, I've made some notes for you, just kind of hitting the high points on repeated measures ANOVA, and it also includes some links to some videos. We'll go through this in a minute when I do a little bit of lecturing. There's also in here some SPSS resources on how to run a repeated measures ANOVA in SPSS. Here's a video demonstration of me running through the analysis, the example that's in the notes here, in running through it in SPSS, interpreting the output. Here is some annotated output. So you can see there's some steps for running repeated measures ANOVA in SPSS, how the data would look like if you entered them in there, and then kind of the output. And I could try to annotate, what each one of these tables is telling you. So you can look at that. It should be sort of self-explanatory. And I talk about it also in the demonstration video here. There's also this link is you can download the data set for the example. If you want to you can practice typing in, compare it to what we have here. And here's a syntax file if you want to use the syntax instead of the pull down menus. I have that there. Also linked in the modules, as always, there is a data analysis assignment you'll see here, and a quiz you can find here. So you can look at the data analysis assignment. It's very similar to the last data analysis assignment. I give you an example research scenario here. here's some data that correspond to that scenario. So you need to enter that into SPSS, and then answer these different questions based on your analyses of those results. And you should be able to find all this information that's asked for in here is talked about in the notes in the readings. So all that should be pretty self-explanatory. If you have any questions, you can always reach out and talk to me. And remember, you can always work in groups on the assignment, so you're not alone trying to tackle this problem on your own either. There's also a quiz here. Remember, you can take the quiz up to 3 times, and it'll keep the highest score. So don't forget about all of those. So let's talk a little bit about the one-way repeated measures analysis of variance. We can kind of think of this analysis really as an extension of the dependent t-test or the paired samples t-test that we discussed in Stats 1. With the dependent t-test, there were 2 levels. There was like a pre-test, post-test type situation. With repeated measures ANOVA, we have 3 or more repeated measures. So we could have like a pre-test, a post-test, and then a follow-up, say like 3 months later or something. So that gives you kind of an idea of what the repeated measures ANOVA is. So we have a dependent variable, sometimes that we're tracking over time, or we could also have like the same group of participants are being measured on the outcome at multiple points in time. Let's look at this example research scenario. We'll be working through this throughout the notes. So a researcher is interested in the effects of caffeine on memory in a group of 5 college students. So she first gives the students 100 milligrams of caffeine and then gives them a memory test. The next day, she gives them 200 milligrams of caffeine and gives them a memory test. Third day, she gives them 300 milligrams of caffeine in a memory test. And the fourth day, 400 milligrams of caffeine in a memory test. The researcher can then test to see whether, the memory scores, their scores on the test is different depending on the level of caffeine consumed. So here our independent variable would be the caffeine consumption, whether it was 100, 200, 300, 400 milligrams of caffeine, and the dependent variable are their scores on that memory assessment. So if we think of this in statistical terms, the null and alternative hypothesis here, the null hypothesis, remember, is usually the hypothesis of no difference. So, the null hypothesis would then be memory does not significantly change depending on caffeine consumption. We could conceptualize then the alternative hypothesis as, memory significantly changes based on the level of caffeine consumption. Or we can put a direction to it, like the memory significantly increases as caffeine levels increase, or memory significantly decreases as caffeine levels increase. So you can see in this example, we have the same participants, the same 5 participants are measured on the dependent variable, the memory test, at more than one occasion, right? So the same five participants are receiving 100 milligrams of caffeine on the first day, 200 in the second day, 300 the third day, 400 the fourth day. And then they're given a memory test each time. So we have 4 different measures of a student's memory assessment, 4 different measures of their memory assessment at 4 different occasions. So that's where the repeated measures come in. So you can see in here, I've linked to several different, other helpful YouTube videos that you might find helpful. So you can check out another example here. Anytime we run a statistical test, we make certain assumptions about the data. Some of these may seem familiar, like the independence assumption. This is basically, observations within each treatment group or each measurement occasion are independent. And basically what we mean by that is that observations aren't influenced like by any other observations. So so one person's score on their memory assessment is impacted by someone else's score on their memory assessment. The normality assumption is usually, it's basically that the population distribution within each treatment condition is normally distributed. Usually we're not too worried about this assumption. It becomes more important as your sample size decreases, mainly because of the central limit theorem. The central limit theorem would say that as our sample size increases, the sampling distribution approaches a normal distribution. And I think generally the rule of thumb is if we have 20 or more degrees of freedom for the error term, we're typically okay with this assumption. If you violate this assumption, you could transform your dependent variable, but then it makes it awkward, interpreting the results again, or you could use an alternative test like the Friedman test that doesn't make the normality assumption. Right now, we're going to ignore it and say that, generally, the repeated measure is ANOVA is robust to violations of normality. The big assumption here, which makes repeated measures ANOVA not as makes repeated measures ANOVA a little more difficult to use in real life situations, is this sphericity assumption. And basically, this assumption says that the variances of all the different pairs of the repeated measure variables must be equal. Sometimes you'll see it said that, both the variances between each pair of variables and their covariances must be equal. That's a stricter assumption called compound symmetry. But the Gravatur and Walnu book kind of breaks this down into two different assumptions. It talks about the assumption of homogeneity of variance and assumption of homogeneity of covariance. Basically, sphericity requires that both of these assumptions are met. So it kind of encompasses both of those things. They just sort of broke it out. The homogeneity of variance is basically the population variances within each treatment are equal. And the homogeneity of covariance is basically what we talked about before, was that the correlation or the covariance among all the dependent variables among the repeated measures are equal. And so the sphericity assumption requires both of these things to be true. The hard part is, in practice, sphericity can be a tough condition to satisfy. You can think about this conceptually. Repeated measures that are closer together in time are usually more highly correlated with each other. So, measurement at time 1 and time 2 are usually more strongly correlated with each other than a measurement at time 1 and time 3. And that then would be a violation of the sphericity assumption, which assumes that the relationship among all the different pairs is equal. And that would be a case where they wouldn't be equal. Measurements closer together in time are more likely to be similar. This isn't a problem. We didn't talk about this when we had the dependent samples t-test, because it's not a problem when your independent variable only has 2 levels, because you only have that one variance or that one relationship to worry about. When you extend to 3 levels, you have the variance between measurement 1 and 2, measurement 2 and 3, and then the covariance between those two. So when your independent variable only has 2 level, sphericity isn't an issue there. It is when you have 3 or more levels, repeated measures there. So we can test for this assumption. There's a test in SPSS. I'm going to butcher the name here, the Malchi test. That is sort of like that Levine's test for homogeneity of variance. It's another one of these tests that you want to fail to reject the null hypothesis. The null hypothesis here is that the variances and covariances are equal. And, you know, violations of, so if this test is significant, it means that indicates that you have a violation of spherosity. And when this happens, the F test in the ANOVA is too liberal. It makes it easier to find statistical significance. There is a correction we can make for this, just like in the between subjects ANOVA. There's Welch's correction for if you violate homogeneity of variance. There are two popular adjustments you can make. We're going to mainly use this Greenhouse-Geyser adjustment, but there's also another adjustment here, this FH adjustment that basically tries to adjust the F statistic for how severe the violation of spherosity is. This HF adjustment has been shown to make too much of an adjustment. So most people recommend using the Greenhouse-Geyser. We can calculate a statistic that quantifies the extent to which our data deviate from spherosity. And this statistic is called epsilon, and it's actually printed in the SPSS output. And so we could look at that to judge how far off from the spherosity assumption we have, you know, the extent to which the covariance matrix differentiates from spherosity. So an epsilon of 1 indicates that we have perfect agreement that our data perfectly match what's assumed by spherosity. Some authors, and you can see the Stevens multivariates test, they argue completely against using formal test of spherosity and recommend simply always using the Greenhouse-Geyser correction. That's their recommendation, is just to always go with the Greenhouse-Geyser recommendation, you know, with that adjusted degrees of freedom in F test. Their reasoning is if there isn't a violation of spherosity, the adjustment it makes is very minor. So it doesn't change the F test too much. But if you do violate it, then it makes a correction to help protect against the type 1 error inflation there. Also, if you do violate the assumptions process, sometimes it's indicating that there's something wrong with your statistical model too. It might be that we need to add a between subjects factor variable, like say maybe we need to look at whether there's differences across gender, because, you know, males and females are reacting differently maybe to the caffeine consumption in our example. This would then make it a mixed design, but that might also then solve the spherosity problem that we're having as well. There's some other things. They're not technically assumptions that we're making, but they're good things to look out for. Kind of data preparation, data cleaning steps we want to take. You know, we might want to graph our data, make sure there aren't any outliers that could greatly inflate the results that we're seeing here. We want to take into consideration issues of missing data. So say we had a student, Lee, came for day 1, came for day 2, skipped day 3, didn't show up, and came back on day 4. With the repeated measures ANOVA, we'd have to throw out all of their data. So someone needs, for the repeated measure ANOVA to be included in the analysis, each subject has to be at every single measurement occasion you have. So we'd have to address those issues or just throw out anybody who's missing. Some of the alternative procedures I talk about in that document, like if you estimated it with a multi-level model, it could include that person who came for occasion 1, 2, skipped 3, is missing and came in 4. It uses what's called a maximum likelihood estimation procedure that can handle missing data on that case. Another approach to handling missing data is what's called multiple imputation procedures. If you're interested, you can read a little bit more about that, or sign up for Stats 3 in next spring, and we'll talk about how to handle different missing data issues. So that's the concept that we cover there. So it's a little beyond the scope of this class, but we'll cover it in the next stat sequence. Here's another video here that goes over different assumptions, and then the assumptions for the repeated measures ANOVA, and then what you might do if you violated those assumptions. I'm not going to read through all of this. You can do this yourself. One of the big advantages of the repeated measure ANOVA design is that the variation among participants that's due to individual differences is completely removed. Because, in this case, each individual is kind of like serving as his or her own control group. And so, repeated measures designs are usually more efficient and more powerful than completely randomized designs or, randomized group designs, or what I call between subject designs. They need far fewer cases to achieve the same amount of power. And the error term in repeated measures design is a lot smaller than the error term in a between subjects design, like in the between. So the error term we'll see in our example here for the one-way repeated measures ANOVA is a lot smaller than what it would be if we treated it as a between subjects ANOVA. There's also some disadvantages to the one-way repeated measures ANOVA. Sometimes it's a lot harder to control different extraneous variables. Carryover effects can be a problem. Sometimes we might want to try like counterbalancing our independent variable. So we might give some participants, say, 200 milligrams of caffeine on the first day. Some get 300 milligrams of caffeine on the first day, to kind of rule out that it was the order that we gave them these the treatments that actually impacted it. If we look here on our example, if we have different experimenters giving the memory test, they may not rate everybody the same, so we could have an instrumentation issue here if their ratings aren't consistent. So say on the second day, students had a big exam where they had to memorize, say, a lot of definitions. Their memory might not, their memory might just be shot, and they're just, I'm trying to remember all this stuff from my exam, and I don't care about your memory test. Sort of things. People could get bored with the experiment. People may not show up for the experiment. Students have memorized the answers on the test, or are starting to they're starting to actually grow in their ability to answer questions on the test. So you can see there's lots of different issues that could arise here. Repeated measure designs also have a generalizability issue. The generalizability of the results is usually a lot more limited in these cases, mostly because we usually have a smaller sample. So the sample size may not be as representative of the entire population. So you just want to ask yourself those sorts of things. The laboratory monitor text does a good job of talking about some of these different issues, and you can read through that here too. I want to work out a repeated measures ANOVA by hand. I'm not going to ask you to do this on the assignment. I'm working through it here so you kind of get an idea of what's going on behind the scenes to kind of I think it gives you a good idea about what's actually happening here. So here we have our 5 subjects. I have the 5 subjects listed. Here are, day 1 we had 100 milligrams of caffeine. Day 2, 200 milligrams. Day 4, 400 milligrams. So here's our first subject, and here are their scores on the memory test with 100 milligrams, 200, 300, 400 milligrams. And here I just averaged across this row. So same thing with person 4. These are their scores for each day that corresponded with how much caffeine they were given that day. Also computed down here the column mean. So this would be the average memory test score across subjects for the 100 milligram coffee. And then here's the grand mean. You can think of it as like the average of the averages. You could average either the row means or the column means, and you're going to get this grand mean. If you remember from the one-way between subjects ANOVA, we can partition the total variation in the dependent variable. We can calculate the total variation in the dependent variable. We call that the sums of square total, or the total sums of squares. So we take the total sums of squares in the outcome. And we can decompose it into 2 parts. Sums of squares that are due to differences between treatment conditions, and the sums of squares that are due to variation within individuals. And remember, in the between subjects ANOVA, the within variation was also our error variation or unexplained variation. So if we wanted to calculate the between, the sums of squares between, we'd basically subtract the average score for each dose. So like, 26.4 from each individual's from the grand mean, because we're looking at between variation. Sorry, we're not going within. So what is the total variation between the different treatment conditions? So we take the variation for group 1, subtract it from the grand mean, and square that difference. And we're actually going to do this. I'm multiplying it by 5 because we would do it for each individual within the group. So we would do 26.4 minus 24.9 squared, 26.4 minus 24.9 squared, and you do that 5 times. So if we're doing that 5 times, we can also multiply it by 5. So that's what we're doing here. So we're taking each one of these column means, subtracting it from the grand mean, squaring it. Remember, so sums of squared deviations. That's how we get then our sums of squares between. So here's our estimate of sums of squares between. So our sums of squares within would then be, we want to take each individual's score, subtract it from the average for that group, and we would square it again. So for instance, subject 1 had scored a 30 on the memory assessment when they took 100 milligrams of caffeine. We subtract that from the average for that condition and square it. Same thing with the next person, next. And then we do the same thing, we'd go for the 200 milligram group. We would take subject one score, subtract it from the mean of that group, and square it. So that's what we've done here, and we get our error, our sums of square within. Remember, for the one-way between subjects and over the F test, would then take these sums of squares divided by the degrees of freedom. We'd have the mean square terms, and that ratio would be our F statistic. In the repeated measures ANOVA, notice that these row means, so participants' average memory score, differs considerably, right? You know, it ranges from about 16 to about 34. So in the random effects ANOVA, we can quantify, this variation. Remember, before we only took variation in the column means into account, variation between the column means and the grand mean, and then the individual scores and the column means. We also have variation that's due to differences within individual level differences. So we sometimes we'll call this variability the sums of squares for the blocks. So we're blocking on each subject. So basically, we can then decompose some of this error variability we calculate, the sums of squares within. We can remove then that individual differences from the sums of squares within by looking at individual variation from their row mean. So we're removing the individual differences from this error term, from our sums of squares within here. So we can split up our sums of squares within. It's composed of our sums of squares for each of the blocks or each of our subjects, plus a residual sums of squares is what they'll call it. And so to calculate the sums of squares for the block, we take each individual's mean score across each dose, the row mean, and subtract it from the grand mean. Right, so we take the row means from the grand means, square the deviation, and then we do that for each one of our repeated measures. It's right, they had 4, this row mean was composed of 4 different measurements. So that's where this formula then comes in. So we can see there's our sums of squares for the blocks. Notice how much, this was a large proportion of the sums of squares within, right? So if we want to calculate the sums of squares residual, we've already calculated the sums of squares within and the sums of squares block. We can, a little bit of algebra, we can rearrange this formula, and we get the sums of squares residual as here, 112.8. So you can see the vast majority of the variability of the within variability was due to individual differences. And now we are able to, with the repeated measures ANOVA, we're able to remove that from the error term. So the error term and the repeated measures ANOVA is going to be this. This would be the sums of squares error that SPSS is going to report, the 112.8. If we would have run this as a between subjects ANOVA, this would have been the error term, or the sums of square error that it would have reported. So you can see we drastically reduced that by removing the individual differences from there. So from here we can compute then, similar to how we did in the between subjects ANOVA, we can compute our mean square terms, which are just our sums of squares divided by the different degrees of freedom. So the mean square residual, the degrees of freedom for it, is the number of participants minus 1 times the number of repeated measures minus 1. So the degrees of freedom for the error term would be 12 here. So there's our mean square error term. We can still get our mean square between, the same as calculated in between subjects ANOVA. And we have then our F statistic is in our mean square between divided by our mean square residual here. And so we'd get an F statistic of around 24.76, which would be highly statistically significant. So this indicates that memory significantly changes based on caffeine consumption. So our next question might be, which specific treatment conditions differed? Now, same way with between subjects ANOVA, we have a significant omnibus F test. We want to follow that up with some post hoc tests, and we'll talk about that here in a minute. We can also get, similar to between subjects ANOVA, we can get an effect size for the repeated measures ANOVA. There are lots of different ones. SPSS reports partial eta squared, so I'm just showing you here how it's computed. You can also calculate an omega squared and partial omega squared values, but you'd have to compute those by hand, so I don't have those, the formulas here for you. But you can see if we were to compute the partial eta squared for this example, we would get a 0.86. So what this is saying is that 86% of the variation in individuals' memory test scores can be explained by the different caffeine dosages. So it's interpreted similar to how we interpret it in the between subjects case. So similar to our between subjects ANOVA, when we find a statistically significant main effect, like we did, we want to follow it up with post hoc test. The post hoc tests that SPSS provides are pretty limited. It really only gives you 3 options in this case. One of them, it's abbreviated LSD, which is least significant difference, which means it's making no adjustment whatsoever. There's the Bonferroni adjustment and the Sadak adjustment. You probably remember those from Stats 1. The Stevens multivariate text here, he recommends using the Bonferroni adjustment. And SPSS will automatically adjust the p-value for you when you use this, so you can still compare your value to the nominal alpha level of 0.05. You don't have to make the Bonferroni adjustment yourself. Some other programs, stats programs, don't make the adjustment for you, so you just have to know what the program's actually doing. If you want a little bit more information on the difference between the Bonferroni and the Sadak method, you can check that out here. And then finally, you can note that you can also get an effect size for each one of your post hoc comparisons for each pairwise difference that you find. You can also compute a Cohen's d, or a standardized mean difference between those two. And it would basically just be the mean difference between the repeated measures divided by the square root of the mean square error term. So we would go back and get this, where's our mean square? Divided by this mean square residual. So you divide it by the square root of 9.4 in our prior example here. Finally, in the notes, I provide you with an example write-up. So how do you write up the results of a one-way repeated measures ANOVA? For all the write-ups, I always start off mentioning the statistical test performed. So in this case, we performed a one-way repeated measures analysis of variance. We'd always discuss whether or not we met the assumptions that underlie the statistical test. Like, if you tested for sphericity, did you meet the assumption? How did you determine whether you met this? If you're going to ignore the assumption and always use the greenhouse Geyser F statistic, just mention that that's what you did, and you can even cite the Stevens citation I gave you for that. Notice in the And the write-up below, so this was, I provided you an example write-up. Here's the citation, the abstract, and their results section here. You notice that they didn't, some of the things I'm saying do, you notice they didn't do that. If you made any adjustments, you would list those. Make sure you list that like I talked about. You'd provide the results of your statistical test, provide an estimate of effect size like partial eta squared, mention any post hoc test. If you did a Bonferroni did a post hoc test with the Bonferroni adjustment, just mention that you did that. They did I think they did a different one down here. Oh yeah, they use home sequential Bonferroni procedure. So you just mention the one that you did, and then if you have any post hoc test, you might want to give an effect size estimate for that test as well. So you can see sort of the example right up there too to kind of follow along. That's all for the lecture this week. If you have any questions, please post them to the message board. Always reach out to me as well. I'm happy to clear up any confusion, and I'll see you next time. Thank you.